Hello, this is Rohan Thakur, one of the undergraduate tutors for MCBC100A.
And today I'll be talking about delta G and its relationship to equilibrium constants in general. I'll follow up later on with a video particularly about ligand binding, which is pretty relevant for the upcoming midterm. But today I'll just be talking about some basic fundamental concepts with equilibrium constants and free energy. So let's start off first by just writing a generic reaction. There's some species R that is transforming into a species P. Here, the reactant is R, the product is P. For any reaction like this, even a more complicated reaction, I can write the equilibrium constant, KEQ, as the concentration of products, here it's P, over the concentration of reactants. Here, the reaction is pretty simple. There's no coefficients. It's not like 2A plus B goes to C. If there were a coefficient, for this reaction, for example, the equilibrium constant would still be C over A and B, but because there is a coefficient with the A, you would include a superscript there, an exponent of 2. But anyway, so for this reaction, the simple reaction, that's the equilibrium constant, KEQ. Now, if I wanted to relate this equilibrium constant to the free energy of the reaction, I would use the equation delta G equals minus RT ln K. So this equation should be pretty familiar to you. I just want to pause here and highlight that this is the form of the equation you should be using in this class. On problem sets, you might have manipulated this equation. Maybe instead of using Ka or Kd or free energy of binding, free energy of unbinding, the minus sign dropped out somewhere. I'd recommend that you do not use the shortcuts, that you don't work from that equation, but you always work from this equation here, because this equation is true in all situations. If you manipulate the equation a little bit, you might make a sign error by using the wrong K or looking at the wrong free energy. This equation is actually pretty fundamental. It's derived from the definition of chemical potentials, and if you want to see that derivation, it's on page 422 to 425 of the textbook. I recommend taking a look at that so you can understand what assumptions went in to make this equation. Another thing I wanted to highlight is that this equation implies a direction. So the way it's written, I'm talking about a certain direction of the reaction. So for example, on the reaction to the left, I'm talking about R transforming into P. Let's assume this reaction is spontaneous. If it's spontaneous, P dominates over R. Therefore, for that reaction, KEQ, if P is greater than R, then KEQ is greater than 1. So going back to this reaction, going back to the relationship above, if KEQ is greater than 1, then the natural log of the product of KEQ is greater than 0. And with a negative sign, this implies that the free energy associated with the forward reaction is less than 0, which matches our assumption of spontaneity. So this is why it's important to work from this equation. Everything makes sense. When a reaction is spontaneous in one direction, the product direction down are the reactants. Therefore, KEQ is greater than 1. Following that equation up there, then delta G is less than 0. Alternatively, we could consider a non-spontaneous reaction. Let's just write that same reaction backwards. Now, this K, let's call it K2. This K has R over P. If we assume that is spontaneous in the opposite direction, then this K is less than 1, which implies that delta G is greater than 0. or that the reaction is non-spontaneous. So that kind of example, it's a pretty simple example, but I wanted to highlight why it's important to use the equation in the form that is up here. And I also wanted to highlight how you could manipulate the direction of the reaction to look at a different delta G or different K than what is given. So for example, if I wanted to go from KEQ to K2, the relationship is pretty simple. KEQ is just the reciprocal of K2. So KEQ is K2 minus 1, or 1 over K2. And similarly, delta G1 of the above reaction is just delta G2 negated.